Okay, we start on a new topic tonight. I hope you all had fun inventing your Simpson's paradox scenarios. And you'll probably find that this new topic, random variables, at least for a while, is considerably more straightforward than what we were doing last week, which was really getting sort of to the lunatic fringes of conditional probability. So, I'm going to start with topic 1, definition and examples for random variables. Random variable is possibly one of the worst phrases ever invented. In much the same way that a guinea pig is not a pig, a random variable is not a variable. And furthermore, it's not really random in the sense that it has nothing specifically to do with probability. What it is, I'll abbreviate it RV, and almost always we will denote a random variable by a capital letter of the sort that's ordinarily used in lowercase for representing an honest-to-goodness variable. This is a function from our sample space to the real numbers. Most of the time, the values assumed by this random variable will be integers, but it's perfectly reasonable to have a random variable that can assume the value pi or e or the square root of 2 or something else that's irrational. We're only going to consider discrete random variables. And what makes a random variable discrete is that it can only assume a countable set of values. Now, countable doesn't necessarily mean finite. The integers are countable, for example, even though there are an infinite number of them. And anything that can be put into one-to-one correspondence with the integers is also countable. So, for example, the rational numbers are countable. The primary example of something that's not countable is either the real number line or even some interval of it. That is, there are uncountably many points in the interval from 0 to 1. There are uncountably many points in this square on the whiteboard and so on. We're going to stay away from that sort of situation. I may sometime teach a course on continuous random variables, but in order to deal properly with those, you really need calculus and specifically multivariable calculus. So I want to stay away from that in this course, in which calculus isn't even a prerequisite. Now, there are some special terms that are worth knowing. If the random variable can only assume a finite set of values, then it's called simple. And if the only values that it can assume are 0 and 1, then it's sometimes called a Bernoulli random variable, and it's sometimes called an indicator function. So now I want to give you a whole lot of values, a whole lot of examples of random variables. I mistakenly said in the outline, here are some examples of discrete random variables, but there are a couple in here that aren't even discrete. And what I'd like you to do is to figure out for each of them whether it's discrete, whether it's simple, whether it's Bernoulli, and then for future reference, whether it's defective. But I haven't defined defective yet, so we'll have to come back to that. And I will put a one-word description next to this so that you can match it up with your outline. But you probably want to have your outline in front of you for these examples. So example A is the number of aces in a bridge hand. You pick up your bridge hand and you look, oh, I've got 3 aces, I've got no aces, I've got 1 ace. That's a random variable because the sample space is the set of all possible 13 card bridge hands, and the random variable is the function that takes a hand and converts it to just one number, the number of aces in a hand. Okay. This is a discrete random variable? Sure. There are only 4 or 5 values that it can achieve. Is it simple? Sure. It has the values 0, 1, 2, 3, or 4. Is it Bernoulli? No. It would be Bernoulli if the question was 1 if I have an ace, 0 if I have no aces. Other examples that fall into the same category, if you're a bridge player, would include the high card point count of your hand. You look up your hand, I've got a 14-point hand, I'll open the bidding. The number of points in your hand is another random variable of the same sort. Okay, next one. Whether a bridge hand includes the queen of spades with the convention that 1 means you have the queen of spades, 0 means you don't have the queen of spades. And another way of characterizing that is the number of queens of spades in your bridge hand. Discrete? Yep. Simple? Bernoulli? Yes. And notice that this corresponds precisely to the event. The queen of spades is in the bridge hand. So you can reformulate the events we've been talking about all in terms of random variables, and some probabilists favor that as a fundamental approach. Next one. You pick up your poker hand and you count the number of pairs. Discrete? Sure. Simple? Sure. Bernoulli? No. Okay, now we get a little more subtle. Someone gives you 1 strontium-90 nucleus. Strontium-90 is a notable component of radioactive waste products, and it sticks around for a good many years and ultimately decays at a more or less completely random time. And my random variable is the calendar year in which it decays. So you may put this in a little test tube somewhere, and in the year 2027, it transmutes into something else. Is that discrete? Yes, because I said the calendar year in which it decays. There are uncountably many instances of time at which it may decay, but if all I ask for is the calendar year, it's discrete. Is it simple? No. The probability that it will still be around after 1,000,000 years is mighty small, but it's not 0. So there are an infinite number of possible values that this random variable can assume. It is not simple, and it's certainly not Bernoulli. Okay? Next one. The number of people whose deaths are reported in a murder mystery novel. And I picked murder mystery novels because a randomly chosen murder mystery plot is a very complicated individual outcome in a sample space. But if the random variable is simply the function that assigns to a murder mystery novel the number of individuals whose deaths are reported, is that a discrete random variable? Sure. In fact, it assumes only integer values. Simple? I think probably yes. It's a little hard to imagine. I mean, a serial killer who can produce more than a finite number of deaths, that wouldn't be a murder mystery. That would be a Halloween thriller. Okay? Bernoulli, no. My experience in these murder mysteries, the minute someone starts investigating, lots and lots of people die. Okay, next one. You're playing darts. Darts is kind of fun because the sample space consists of all the points on the dartboard, and sometimes some of the ones that aren't on the dartboard either. And so here the random variable is the distance from the center of the dartboard at which the dart hits. Is that a discrete random variable? No, because that is a real number, but there are uncountably many different distances at which it can hit. So that's one that we can't handle. Since it's not discrete, it's certainly not simple, and it's certainly not Bernoulli. But now we come to G, where we've got our dartboard neatly divided up into rings, and the ring shows you the score you get from the dart. The score obtained when throwing a dart at a dartboard. That discrete? Sure. And in fact, it's these rings that make darts a manageable pub game. If every time someone threw a dart, someone had to rush out with a measuring tape and try measuring to the nearest millimeter the distance from the bullseye at which the dart had hit, it would be considerably harder and less interesting to play darts. And basically, a conventional dartboard is a device for introducing a discrete random variable into darts. Is it simple? Yeah. Is it Bernoulli? No. It could be Bernoulli if you got 1 point for hitting the board and 0 if you missed. But in conventional darts, it's not Bernoulli. And now the last one. You walk into a casino. You start with $1,000, and you all know that your gambling is a random process. And the random variable is the number of minutes after which you leave if your leaving criterion is that as soon as you've doubled your initial stake, you go home a winner. Is that a discrete random variable? Number of minutes rounded up. That is, if after 10 minutes and 37 seconds you've got $2,000, that's the 12th minute and you walk out. Discrete? Sure. You've hit on the problem, but in the wrong place. We're getting awfully close to the bottom of the board here. So, yes, this is discrete. Is it simple? Yeah, Jerry?
Well, I worked out the problem in the text involving Gambler's Ruin.
Yes.
And it is sure that at some point or other you'll either win the amount, or you'll lose. So it should be simple. But in theory, it seems to me it could go on forever.
No, wait a minute. It is simple if there are only a finite number of possible outcomes. So you'd have to be able to guarantee that within X minutes, you're either broke or you go home a winner. And you certainly can't do that. So it is discrete, but it's not simple. It's not Bernoulli. And now let me introduce the last word, defective. Because in most cases, the probability for all the values of a random variable sum to 1. And if the random variable has that property, it's known as proper. If it doesn't, it's known as defective. In order to explain exactly why this last random variable is defective, though, I'm going to have to introduce some more terminology. So I'm now going on to topic number 2, event space for a DRV. The reason it's abbreviated, of course, is event space for a discrete random variable has more than 26 characters in it and won't fit in the software that attaches the topic headings to the videos. So I have abbreviated it DRV. Since we've been calling events A, let me first introduce an event named A sub x. And that means that the random variable capital X has value little x. So, for example, if capital X is the number of aces in your bridge hand, and you pick up your hand and see the ace of spades and the ace of hearts, but neither of the other two aces, the event A sub 2 has occurred. If your strontium-90 nucleus finally decays in the year 2050, the event A 2050 has occurred, and so on. This terminology is consistent with what we've done before, but it's not entirely standard. What's usually done is to introduce something called the probability mass function. This is always denoted by a lowercase letter. It is usually subscripted by the random variable to which it applies, though on occasion, if there's only one random variable kicking around, this subscript will be left off. And it's always an argument. It has one argument, which is the value that might be assumed by that random variable. And this is, by definition, the probability of the event A sub x, or the probability that the random variable x assumes the value little x. So, for example, with aces in a bridge hand, if you pick up your hand, you apply the function capital X to count the number of aces, and the value of the function turns out to be 2. The probability of that event is what I mean by f sub little x of 2. Now, the last pieces of terminology. If the sum over all outcomes is 1, then the random variable is called proper. Otherwise, it's called defective. Now, what you're going to learn when we study Gambler's Ruin and random walks is that if you play in a fair casino, and if you have a bank that's willing to back you with infinite amounts of credit, the probability of eventually being $1,000 ahead is, in fact, 1. It may take a very long time. So in that case, the random variable for when you leave would be proper. But if there's any house percentage ever so slight, the probability of leaving after 1 minute, after 2 minutes, after 3 minutes, so on, when you sum that all up, it sums to an amount less than 1, a calculable amount less than 1. This is still a perfectly good discrete random variable, but it has the problem that there's some very significant probability that you might, in effect, take forever. So the probability that it will take infinite time to do this, that is, it will never happen, might, in practice, be 0.9 or something like that. Nonetheless, such a random variable would still be a perfectly good discrete random variable if you round up to the nearest minute. Okay, I'm now ready to move on to number 3, bridge and poker, and give you some examples of how to use the counting techniques you've already learned to work out these mass functions. So we got bridge and poker. And I said glibly in the outline, it is easy to work out the mass function for the number of aces in a bridge hand or for the number of pairs in a poker hand. I said that because Sturzacher says it. And then when I actually went to do it, I decided, well, maybe it's not that easy, but let's give it a try. So we'll start with bridge. X is equal to the number of aces in a bridge hand. And while the mass function for this random variable does depend on the assumption that the deck has been well shuffled, the random variable itself does not. The random variable itself is just a rule that says, you look at your bridge hand and tell me one thing, how many aces has it got in it? Okay, let's work out f sub capital X of 4. That means the probability that the number of aces in your hand is 4. If you've got all 4 aces, how many ways are there of filling out your hand?
13 choose 9. 7. No, 52 choose 9, sorry. 48 choose 9.
48 choose
9.
9, thank you. You've got 9 cards that are not aces. They have to be selected from the 48 remaining cards in the deck. There are 52 choose 13 possible bridge hands. So with the counting techniques you've learned, you can start working out mass functions like this. Let's do a couple more because there's an interesting calculation that arises. What about f sub x of 3? That's the probability that the number of aces in your hand is 3. The denominator is always 52 choose 13, but what's the numerator now? So there's 4 choose 3 for which aces you have, and 48 choose 10. I'll do one more so you see the general pattern. F sub x of 2. Now you've got 2 aces in your hand, so in the numerator we have 4 choose 2 for the number of ways of selecting the 2 aces you have, and then 48 choose 11. Now here's the problem. When you add up f sub x of 4, f sub x of 3, f sub x of 2, f sub x of 1, and f sub x of 0, what do they have to sum to? 1, right? Okay. This is a proper random variable. There are 5 possible outcomes, and their probabilities have to sum to 1. And it's not entirely obvious that that's so. So here's a cute trick for seeing this. Suppose you take 1 plus x to the 52nd power and expand it by the binomial expansion. That's certainly the same as 1 plus x to the, I want to write it in the opposite order, 1 plus x to the 4th times 1 plus x to the 48th. So far, so good? Everyone will agree with me? Now, let's look at the coefficient of x to the 13th. Okay, here we go. We've got 1 plus 52x plus dot 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 plus something times x to the 13th. What's the coefficient of x to the 13th? (52) choose 13. So lots and lots of terms here. There are 53 terms, but the only one we're interested in is the term in x to the 13th, which has a coefficient of 52 choose 13. Now let's look at this side. 1 plus x to the 4th is easy. That's 1 plus 4 choose 1, x plus 4 choose 2, x squared plus 4 choose 3, x cubed plus 4 choose 4, x to the 4th. Right? And now this next one has a bunch of terms that are of interest to us. It starts 1 plus 48x. And sooner or later, we will roll around to a term with x to the 9th in it. What's the coefficient of x to the 9th? 48, choose 9. And the next term will be 48, choose 10, x to the 10th, somebody just saw it, plus 48, choose 11, x to the 11th, plus 48, choose 12, x to the 12th, plus 48, choose 13, x to the 13th. Okay, now let's equate the coefficients of x to the 13th on both sides. Here we have 52, choose 13, and that's equal to the sum of 5 terms, isn't it? Let's first do the one where we have the x to the 4th here. That's got a coefficient of 4, choose 4, which is 1, and that gets multiplied by what over on the other side? The 48, choose 9, doesn't it? Because 4 plus 9 is 13. Okay, now we've got this 4, choose 3, x cubed. This x cubed has to be paired up with x to the 10th, and the coefficient of x to the 10th is 48, choose 10. Here's this numerator. Here's that numerator. I'll do one more just so you get the general idea. Another way of getting x to the 13th is by multiplying 4, choose 2, which is the coefficient of x, 4, choose 2, x squared, by what? 48, choose 11, x to the 11th. And there are 2 more terms, and you will see that these 5 terms are the numerators in my mass function. When we add them all up, they add up to 52, choose 13, which is the denominator. So this mass function, which is obviously proper from the description of the experiment, in fact, turns out to be proper when you work it out. A lesson to be learned from this, which you may have learned from the original Munchkin problem, is a lot of times if you have a bunch of outcomes which partition the whole event space, so that one and only one of them has to happen, it's a good idea to calculate them all independently, add them up, and make sure they sum to 1, because if they don't sum to 1, you've done something wrong. You have a question? Yeah.
An observation. Yeah, it is a question. Is it legitimate to argue the other way around when you know that you have, by the nature of the problem, partitioned the event space properly, to use that to prove the identity? Because it has to sum to 1?
I would say so, but you remember my PhD is in physics, not in math, so some might disagree with me. Physicists are inclined to say, if on the basis of the real world something is certain to equal 1 and you have an expression for it, that expression sums to 1 and that's the proof. I would say a combinatorist would want to see this proof. Okay, much the same thing works with poker, though I have to disagree slightly.
Actually, I have a question. Just that the last equality, how did you set that? The 52?
This thing? I said each side of this is a sum of terms from a constant term up through a term involving x to the 52nd. If 2 polynomials are equal, the coefficients of each power of x is equal. So in particular, the coefficient of x to the 13th has to be the same on the left-hand side as on the right-hand side, because this is the same polynomial in x on both sides. Okay? I will admit I wasted a certain amount of paper before this proof occurred to me. Now, for poker, the random variable is the number of pairs in a poker hand, and you have to be a little bit careful about this to make it proper. Everyone is going to agree, oh, shame on me. I have used capital F's here and they should all have been lower. So everyone will agree that it should say little f sub x of 2 is equal to the probability of the poker hand that's called 2 pair. And Durango, Bill, and Sturzacher both say that's roughly 0.048. F sub x of 1, that's the probability that there's 1 pair in your poker hand. And that's not just the probability of the poker hand that's called 1 pair, because if you get a full house, that has 1 pair in it. Sturzacher is still right to the number of decimal places that he's quoting, but you've got to include the full house. And then the probability of 0 pairs in your poker hand, that's not what Durango Bill calls no pair, because if you pick up a royal flush, the 10, jack, ace, king, queen, 10, jack, queen, king, ace of spades, say, and you look at your hand, how many pairs are in it? None. You got a royal flush. So the probability for 0 is best calculated as 1 minus the probability for 2 pair minus the probability for 1 pair. This is the sum of the Durango Bill's probability for all types of poker hands except 1 pair, 2 pair, and a full house. Well, I've talked a bit about binomials already, and I'm now set to go on to topic number 4, which is named binomial distribution. Oh, that gives nice contrast, doesn't it? And distribution is another of these terms that is not entirely a happy choice of word. A distribution really refers to a mass function for which there is a reasonably simple formula. And a random variable is said to have the binomial distribution if the formula for it involves the binomial coefficients that show up in a binomial expansion with positive exponent. So let me give you an example. Here's a random variable, I'll call it y, and I'm going to define y to mean the number of heads in n independent coin tosses. And just to keep things reasonably general, let's assume that the probability of a head is represented by p. It may or may not be precisely 1/2. It doesn't make any difference. Now we can work out the mass function. The only thing new here is the use of terminology. This is a problem that you could have solved some time ago. This means the probability that this random variable y assumes the value r. That is the probability of the event. You toss this coin n times and it comes up heads r times. And we know perfectly well how to work that out. First, the probability that r specific tosses will give heads is p to the r. The probability that the remaining n minus r tosses will all come up tails is 1 minus p raised to the n minus r. And when you look at the whole sequence of n tosses, there will be r heads included among these n tosses. What's the number of ways of selecting the r positions where the heads occur?
N choose R.
N choose r, because you're choosing r of n positions to put the h's in. And so there's the mass function. This is said to be the mass function for the binomial distribution, and the term binomial distribution really refers to this formula for the mass function. You will be learning about the binomial distribution, the Poisson distribution, the negative binomial distribution, and the geometric distribution, and that's about it. But it turns out those four distributions show up in a whole lot of real-world experiments. So if you understand those distributions, you've got discrete probability well under control. If you study continuous random variables someday, you will also learn about the normal distribution, the infamous bell curve, which has the property that the random variable can assume uncountably many values, and which therefore, thank goodness, falls outside the scope of this course. Otherwise, I'd be teaching you how to evaluate double integrals involving e to the minus x squared in various places. Now, here's a good example of the point that Jerry brought up earlier. This mass function has to be proper, doesn't it? You toss a coin n times and add up the probability of 0 heads, 1 head, all the way up through n heads. Since there has to be some number of heads, you've included everything. You've got the whole event space, and the mass function has to sum to 1. And it follows that the sum from 0 to n of this mass function, which we can write like this, the sum from r equals 0 to n of n choose r, p to the r, 1 minus p to the n minus r, that has to equal 1. And I guess I will back up what I said on impulse a few minutes ago. I would say, for most physicists, this is a reasonable proof of the binomial theorem. I think for a mathematician, it really isn't. But if you ever have to convince someone from scratch of the truth of this sum, somebody's never seen it before, somehow they skipped 10th grade and never learned the binomial theorem in high school, this is probably the easiest way to convince someone that this sum equals 1 that you'll ever find. You say, look, it describes this experiment. Something has to happen in this experiment, so the probability is summed to 1. You've agreed that each of these things, each term represents the probability of getting a certain number of heads. Add them all up. You have to get 1. Okay, now we're going to do the geometric distribution. And for the geometric distribution, I need to display this little image here briefly. And I've got to reach into my magic bag. And put a die, pull out a die. Okay. This is topic number 5, geometric distribution. And I am going to introduce very straightforwardly a source of confusion that arises sometimes on exams and alert you to something you have to look out for, because there are two different random variables that are said to have the geometric distribution. One is 1 greater than the other, and whenever you see a problem involving the geometric distribution, read very carefully until you find the preposition that indicates which of these two cases we're talking about. Here's the mass function I'm going to write down. The random variable with a geometric distribution is called capital Y. And the probability that this random variable has the value R is 1 minus q times q to the r minus 1. It is my understanding that in probability and statistics courses where students don't like to think, a lot of time is invested in memorizing formulas like this, plugging numbers into them, and applying the correct terms to them. And here's what you got to look out for. Here is what I mean by y in this case. This is the number of times you roll a die until a 6 occurs. This is the Scheherazade problem again. So I roll a die, got a 4. Roll a die, not a 6. And then on the third try, I got a 6. What's the value of the random variable y for that particular outcome? 3, because I said until. And let's check that this formula is right. The probability of rolling something other than a 6, which is q, is 5/6. So I need a 5/6 squared, 5/6 raised to the 3 minus 1 power for the 2 times that I don't roll a 6, and then a 1 minus q for the time I do roll a 6. This is exactly the sort of infinite series that you folks were summing very, very successfully on the quiz to figure out who was the winner in various duels. Now, this is what you got to look out for. Here's another random variable. I'll call it z. The number of times you roll a die before the 6 occurs. Okay, I'm going to do this again, and I want you all to tell me the value of y and the value of z. Remember, these are functions from the sample space to the real numbers. Okay, what was the value of y?
11.
What was the value of z? 10. Okay? So z is equal to y minus 1. And if I write down the mass function for z, f sub z of r is equal to 1 minus q times q to the...
Minus 2.
No, gone the wrong way. R. Because I need R non-6s and then the 6 that ends the thing. Both these mass functions are proper. If I sum this one over the right limits, I get 1. But the smallest value of R here is 1. Because you have to roll the die at least once to get a 6. Whereas here, the sum of the mass function for the random variable z from 0 to infinity, which is 1 minus q times the sum from r equals 0 to infinity of q to the r, is, of course, 1 minus q over the sum of this series, which is 1 over 1 minus q, which is 1. Now, an interesting thing about this random variable is that it's not simple, as was becoming painfully apparent when I did that last experiment. There's no finite number of rolls after which I can guarantee to have a 6. So there are an infinite number of possible outcomes for this random variable. When I say geometric random variable, I may mean this, I may mean that, because the same is true of textbooks. You have to read to see whether it says until you count the 6 that breaks the sequence, or before you don't count the 6 that breaks the sequence. And the same thing is true for topic number 6, which I can sneak in before the break. This is negative binomial distrib, after my wife counted letters and said, if you put distribution, you've got more than 26 there. My wife's cousin, a retired Navy judge, had a dog that tended to misbehave. And when we complained, he always cited the legal maxim, every dog gets 2 bites. So this is the classic example of the negative binomial distribution. Every day, the postman comes up the walk, Fido goes out and growls, and with probability P, Fido bites. And the question is, how many days can the postman come up the walk until Fido bites for his second and last time and goes off to the pound? So this is like the geometric distribution, only you're looking for 2 things. I'm not going to look for 2 6s because it might take all night, but I can do it with 2 odd numbers. So I roll the die. 1, 2. In that case, the value of the random variable was 2. The number of rolls until I have 2 odd numbers. Let's try again. 1, 2, 3, 4. That time the random variable was 4. So you get the general idea. And although in both these cases the odd numbers were consecutive, that's not a requirement. I just keep looking until I've seen 2 random numbers. The total number of rolls it takes to do that is my random variable. Now this one is a little bit tricky to work out in general, but it's nice to be able to work it out in general, because in working it out in general, you get the negative binomial expansion by a much simpler technique than the one I used earlier. You may, though probably don't, recall that I got the negative binomial expansion by expanding 1 minus x into an infinite series, 1 plus x squared, and then I multiplied together n copies of that infinite series and cleverly managed to extract the coefficient of a specific power of x. But here's another way of doing it. Let's suppose we're just rolling for a 6, and let me write up exactly what I mean. Okay. This one, just to keep you on your toes, I'm going to say y is the number of non-6s, which I'll denote by x, before I get n sixes. So I'm going to roll a die again and again and again. I stop as soon as I've rolled a 6 n times, and the value of the random variable is the number of non-sixes that showed up. That's like saying that the random variable for Fido is the number of times the postman comes up the walk and doesn't get bitten before Fido goes to the pound. Okay? We can work this out. We got a sequence of rolls here. And then we've got the last roll. What does the last roll have to be? A 6. Now, I want to work out f sub y of little r. And so there are going to be r x's in here. And how many 6s are there going to be in here? N minus 1. For a total of r plus n minus 1. Everyone happy so far? Now, let's write down the mass function. I will denote by Q the probability for a non-6. So, we have to roll r non-6s in order for this random variable to have the value r. And how many 6s do we have to roll?
N minus 1.
No.
N.
We have to roll n 6s. We count this one. Now, there are lots of different ways we can intersperse the 6s and the x's. But basically, out of these r plus n minus 1 positions, we have to select a set of them in which we put an x. So the binomial coefficient is r plus n minus 1, choose r. Now, that's the most conventional way of writing this. And last year, a student in the course came to me and said, Paul, I'm really confused. I've got 3 different textbooks here, and they got 3 different formulas for the negative binomial distribution. Which of them is right? And of course, they were all right. They used different symbols to mean different things, and in one case, they did this. This binomial coefficient is exactly the same as that binomial coefficient. They're both this factorial over that factorial times this factorial. This one has the advantage that the thing in the denominator is not a function of r, whereas over here it looks as though both sides of the system are functions of r. So you can do it either way, and in any case, the sum from r equals, okay, what to infinity? You tell me. What's the smallest possible value for r here? 0. Because the first time I tried this, remember I got 2 odd numbers without ever rolling an even number. So the sum from r equals 0 to infinity of r plus n minus 1, choose r, q to the r, 1 minus q to the n is equal to 1. And I think that's actually a fairly good proof of the negative binomial theorem. Some would say, no, you have to prove this directly. What this is a proof of is the fact that the probability that you will go on forever is 0. So that's a matter of taste. Okay. No, I cannot sneak the next one in. I have 5 minutes, and I'm not going to use any of them. We'll take our break now and come back to the exponential function. Homework coming in here. I have a few unclaimed. Okay. I'm going to start off with topic 7, exponential function. My hope is to get to the end of this outline with maybe 20 minutes left and spend the last 20 minutes talking about the computer project, because the subject of the first computer project is random variables, and you're in a position to get going on this. Now, why do we need the exponential function? Answer, mainly because this wouldn't be a respectable course in discrete probability unless I talked about the Poisson distribution, and you can't talk about the Poisson distribution without the exponential function. Some of you will have seen this before. Others will not have seen it. I'm going to try to do a completely self-contained treatment, and the definition I'm going to use is probably not the one you learned in your calculus course. My plan is to prove a definition that you may have seen as a theorem based on this one. But here's my definition. The exponential function exp of x, frequently written as e to the x, is defined as the sum of the infinite series 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus ... which means just keep adding on terms like this. They're guaranteed eventually to start getting smaller and smaller very, very fast, and you can approximate this function as well as you might like to by keeping enough terms of this sequence. So this is of this series. So this is a perfectly good definition. Those of you who encountered the exponential function in calculus probably saw it defined differently, and then this result was proved to you as the Taylor expansion of the exponential function, but it serves perfectly nicely as the definition. Since there is nothing in this formula that justifies this notation with an exponent, I have the obligation to prove to you the addition formula, exponential of x plus y equals exponential of x times exponential of y. And of course, if I write it like this, I run the risk that you'll think, why do you need to prove that? That's the law of exponents. We learned that back in high school. Everyone knows that. It is not at all obvious from the definition that I'm using that the law of exponents applies in this case. And I'm going to prove it largely because it's a good exercise in working with double sums. And there are going to be 4 or 5 other cases where we have to work with double sums in this course. I was burned badly last year when I put a double sum question on the second quiz. I won't make that mistake again, but I would still like you to try to learn how to interchange the order of summation in a double sum, and this is a wonderful example of it. So, here's my proof. The exponential of x plus y is obtained by substituting x plus y into the definition. So this is the sum from my outer index is going to be r. r equals 0 to infinity of x plus y raised to the rth power over r factorial. Everyone's happy with that, I trust. And now what can I do with my individual x plus y to the r? What famous formula beginning with B can you apply to this? Binomial. Let's do a binomial expansion of it. Okay. Now, the trouble with doing a binomial expansion is 1 over r factorial can come out, but then we've got another sum over some index, let's call it I, running from 0 only up to r of r choose I, x to the I, y to the r minus I. Everyone agree? This is the correct expansion of x plus y raised to the r power. And what I need to show is that this mess is equal to the product of the exponential of x by the exponential of y, and that's not at all obvious. Now, I'll tell you how I do these things. I do these things by drawing pictures, and I encourage you to do the same. And because I risk otherwise running out of whiteboard space, I'll have to sacrifice that definition temporarily. I'm going to draw a lattice of points, and I'm going to label these things I and j, because what I want to do is to set j equal to r minus I, so that r is equal to I plus j. And let's look at all the different terms we have in here. We're going to get one term where I and j are both 0, aren't we? That's the one where we expand x plus y to the 0 power. That will give us the 1. And then we have x plus y to the first power. That will give us one case where I is 1 and j is 0, and one case where j is 1 and I is 0. And those both came from r equals 1. And then when we expand x plus y squared, we will have a term involving x squared, where I is 2 and j is 0, and one involving xy, where I and j are both 1, and one where j is 2 and I is 0, and those all correspond to r equals 2. So you get the general idea? As we go to bigger and bigger values of r, we fill in this lattice of points. Now, we're summing all the way from r equals 0 to infinity. Is there any point in that quarter of the plane that doesn't get hit eventually? No. So that means if we think of summing over I and j, we're summing over all values of I and j from 0 to infinity. So here's another way of writing this sum. The exponential of x plus y is equal to the sum with I running from 0 to infinity and j running from 0 to infinity. So far, so good? That'll give us all these points. If we stopped at a finite value of r, we'd have a real mess. But because r goes to infinity, you pick a point, sooner or later, we're going to get a term with the value of x to the I and the value of y to the j corresponding to your term. So what have we got? We've got 1 over r factorial. Well, having changed this to a j, I should really substitute for r. So I'll write that as 1 over I plus j factorial. And then I've got this binomial coefficient, which is I plus j factorial divided by I factorial times j factorial times x to the I times y to the j. Does everyone see what I've done? I've done two things. First, I have replaced r by I plus j, j by r minus I. I've written everything in terms of j instead of r. That's the easy part. And then I've done the hard part, which is to figure out that in order to do the sum, where I sum over r all the way up to infinity, but only over a finite range of I for each r, I have to sum over both I and j all the way from 0 to infinity. Wonderful. This cancels. So now the thing we're summing is a product of two terms, one of which involves only I and the other of which involves only j. And so I can write this as the sum from I equals 0 to infinity of x to the I over I factorial multiplied by the sum from j equals 0 to infinity of y to the j over j factorial. Okay. How many of you studied multivariable calculus? Okay, the rest of you can tune me out. I'm going to make this easy now. This is just like changing order of integration in a double integral. And when you do that, you have to rewrite the integrand in terms of the new variables, and then you have to figure out your region of integration and express its limits in terms of the new variables. And for some reason, people find it much harder to do this in the discrete case than in the continuous case where you're dealing with limits of integration. Someone who is given an integral over this triangle where first you do the integration over y and then do it over x and ask, redo this integral so you integrate in the opposite order and can do it. Been there, done that. Those are easy. Give them a problem like this. They spend hours and say, I just don't see how to do this. But it's the same basic idea. And whether you're doing the integrals or the sums, the hard thing is getting the limits of integration right. And the obvious way to do that in the integral case is by drawing a picture of the region of integration. My message is, even though it's not so obvious to do it, if you draw a diagram of all the points over which you're summing in the discrete case, you have a very good chance of getting the limits of summation right. And if you don't draw that picture, you have a very high probability of getting them wrong. Okay, I've got one more formula to prove for the exponential function, and then we will be done with this.
Erase that?
Oh.
No, that's okay. Just tell me how you use the picture.
The way I used the picture was this, Sue. What I said was, as I thought about what this meant, I filled in all the points on the picture. Having convinced myself that every point with integer coordinates was going to get filled in, I then said, this picture convinces me that I sum independently over I and j from 0 to infinity. We'll see some other more interesting cases later on where you're summing initially over something, say, from n to infinity, and then after you order it, you're summing over one of the variables only from 0 to n, which is more manageable.
Okay. All right.
Yeah, Katie?
Yeah.
Restrictions on I and j? You've been talking about them as though they're natural numbers, and I wonder, is there any
Yes, I mean absolutely by this notation. I assumes all integer values from 1 to infinity. Yeah, Dana?
You make some brief noise about absolute convergence if you're going to...
No, I'm not going to make any noise about absolute convergence for a while. In a couple of weeks, I have an absolutely marvelous example where I describe an actual gambling game we could play. I show that the expectation is undefined because the series is only conditionally convergent, and then explain why this game is fundamentally meaningless. But I don't want to talk about absolute convergence until I have examples that our formalism will deal with where absolute convergence makes a difference. So, and there are a couple of cases where Sturzacher proves things, and he says, I've got to prove the absolute convergence, I've got to prove the absolute convergence. Don't worry about that. If you've never heard of absolute convergence, don't worry about it at all for the next couple of weeks. Until further notice, everything converges, and it converges absolutely. And I'll warn you if there's anything tricky. Okay, so I need one other property of the exponential function, because it's going to be the key to solving a couple of problems. That showing up okay against the now rather purplish background? Okay. I need to prove to you that the limit as n approaches infinity of 1 plus x over n to the n power is the exponential of x. This is a very popular definition of the exponential function, but having used a different exponential definition, I have to prove this as a theorem. And here's how I'm going to do it. I'm going to look at the term in x to the k. And I should fuss about absolute convergence here in order to convince you that this proof is valid, but I'm not going to. I'm just going to say, in order to prove that this is equal to that infinite series I just wrote down, I'm going to say, let's focus our attention on one specific term in the series, the one that has an x to the k in it. I'm going to convince you that in the limit as n approaches infinity, the coefficient of that term in this expansion is equal to the coefficient that was in my definition, and here's why. Well, we got the limit as n approaches infinity of the term in x to the k in this expansion. Okay, let's work out what that is. What is the binomial coefficient that shows up? N choose k. And then we have x over n to the k, and 1 to the n minus k, which doesn't make any difference. Okay? Now, n choose k. I'll pull out a 1 over k factorial. Okay? And then the n factorial over n minus k plus 1 factorial, I'm going to write as n times n minus 1 times dot, dot, dot times n minus k plus 1. Fair enough? There are k terms here. And I've got k factors of n in the denominator. Now, k is fixed. N is going to infinity. For any fixed value of k, what's the limit of the ratio of n minus some number smaller than k over n? 1, right? So all of these things go to 1. Each of them individually goes to 1, and there are only a finite number of them, namely k. And I've still got my x to the k. So this limit is x to the k over k factorial, which is precisely the term in the series that has x to the k in it. For those of you who like to be fussy about your calculus, I will admit I'm interchanging limits here, because what I'm saying is first I'm letting n go to infinity, and then I'm getting a specific coefficient in an infinite series. So when I sum the infinite series, I'm going to have very, very large values of k. How can I justify that? And the justification is this double sum converges, this double thing with the two limits converges absolutely, so I can muck around with the order of taking limits any way I want. And if this were a course in calculus, I would have an obligation to discuss that further. This is not a course in calculus. This is just a formula we need. Many people wouldn't even bother to try to prove it. This is a pretty good proof. So now we can use this. I'm going on to topic number 8, Poisson distribution. No comments about sounds fishy to me. And this will also show up in a wonderful dog bite problem, which I think Sturzacher cites data from Birmingham, England, or something like that, where on with 1,241 postmen, there were 346 cited incidents of dog bites. And the problem is to estimate the probability that a specific individual postman was bitten precisely twice. You can do this problem exactly by using the binomial expansion, but the Poisson distribution gives a very nice approximate solution to this sort of problem. Tonight I'm going to introduce this without any hint about what it might be good for. Just give you the definition. It's just another mass function. The mass function for a random variable x that has the Poisson distribution is given by this formula. E to the minus lambda, lambda to the x over x factorial. And you can see this exponential function shows up in here. And you look at this and say, oh, this must have a lot to do with the exponential function. No, it has very little to do with the exponential function. This is here to make the probability sum to 1. And here's why. Let's check that this is proper and not defective. The sum from x equals 0 to infinity. I'm using x, by the way, this is apropos of the question you raised, Katie. I'm using x here because the textbook uses x. I find it a little unnerving to have an index of summation that assumes only integer values called x. But I think my notation will be consistent with the textbooks in any event. E to the minus lambda times lambda to the x over x factorial. Okay. If that sum is equal to 1, this is a proper rather than a defective distribution. This is e to the minus lambda, which is a constant and factors out, times the sum from x equals 0 to infinity of lambda to the x over x factorial. Doubly bad because I was talking just a few minutes ago about exponential of x. Now I'm using x as a variable of summation. But based on what you just learned, what is the sum of that series? E to the lambda. Right? So e to the lambda times e to the minus lambda is 1 because of the addition formula that I just proved. And so the results I just proved indicate that this Poisson distribution is gives a proper mass function. Yeah, Jerry?
One of the few things I remember about a stat course I took 10 years ago here is that was first introduced by a veterinarian in the Prussian army about horse kicks.
Oh, okay.
That's according to Joe Harrington. That's and it has nothing to do with Poisson either.
Well, that's probably another example of Stigler's law of eponymy. Yeah. I mean, once you know Stigler's law of eponymy, the one thing you can be sure about is that this was not invented by Poisson. Okay. One more new idea, so I'm going on to number 9 now. The distribution function, probably the only header where both distribution and function were written out in their entirety because there were no modifying adjectives. I'm almost getting to the point where I wish I had a white pen to write on this board with, but we'll bring in the closer now and try switching to black. That's not very good.
Green was good.
Green was good, okay. So far I've talked about mass functions, and I guess I should explain what mass has to do with this. It could be that the subject was developed by the Jesuits or something like that, or it could be that the subject was developed by people who had some knowledge of physics. The latter is the actual explanation. And here's the sort of problem that shows up in physics. You have a uniform massive rod, and then you attach point masses in various places. So you have mass capital M distributed all along the rod, and then these point masses. And in physics, one quickly learns to deal with this by talking about the density of the continuously distributed matter and then the individual masses. So the terms have come over into probability theory. You use probability mass function when there are only a countable number of points that have probability associated with them. That's like having discrete masses in physics. And you use probability density function when the probability is all smeared out the way the iron is smeared out in a uniform iron rod or something like that. We won't have occasion to talk about density functions because we're only doing discrete probability. So this mass function is not in contrast to anything else we're going to be considering in this course. It is, however, in contrast to the distribution function. The distribution function is almost always denoted by a capital letter. And the usual convention is if you use a lowercase f for the mass function, you use a capital F for the associated distribution function. And it's just another piece of shorthand. This is the probability that the random variable capital X assumes a value that's less than or equal to little x. And this less than or equal is important because we're talking discrete probability, and there's going to be some finite probability that capital X is exactly equal to little x. If you're dealing with continuous probability, the distinction between less than and less than or equal to should be irrelevant. I had an argument about this when I was putting the placement test together for the statistics course, because this involved something that was clearly continuous, and the issue was less than or equal to 0.15 versus less than 0.15. And I said, if it's continuously distributed, there's no practical distinction between those. And you can't ask a question that tests the distinction. The answer I got, oh, yes. In the one-sided kangaroo tail test, it says that this is significant if it's less than or equal to 0.15. And it's very important to know that if it's precisely 0.15, then the result is significant. I said, well, that's why I teach probability, not statistics. But we're dealing with things. There's a significant probability that capital X will actually achieve the value little x, and this less than or equal, which is always there, is important. Now, the problem with this distribution function is that in many cases, there's no simple formula for it. For the binomial case and the Poisson case, we have a pretty easy to write down formula for the mass function. But there is no corresponding simple formula for the distribution function. Surprisingly, for the geometric distribution, there will be one, and we'll make quite a bit of use of it. But I will work a couple of messy examples to show you this, but first some general cases. Try this one. What do you get if you sum up the probability, in the opposite order, the probability that x is less than or equal to little x, and the probability that random variable x achieves a value greater than x? 1, right? Notice I need less than or equal to and greater than, so I don't count x twice. These sum to 1, and therefore we have a conceivably useful formula that the probability that x is greater than little x is equal to 1 minus the value of the distribution function. Here's another one. Here's B, here's A. The probability that x is less than or equal to B is equal to the probability that x is less than or equal to A plus the probability that x is in between A and B, and let's get this right. Should this be less than or less than or equal? That's a strict inequality, and this one is less than or equals. Okay? So that tells us that the probability that x is in the range between A and B, including B but not A, can be written as the difference between the distribution function evaluated at B and the distribution function evaluated at A. That is, as f of B minus f of A. My message is that there are lots of probabilities of events that you might want to talk about that are conveniently expressed in terms of this distribution function. It's an annoying fact that you don't often have a formula for the distribution function, but it's nice to think that if you did have one, you could calculate other things from it. And one last one. This one comes with a caveat. If x assumes only integer values, this is often the case, but I have not been assuming it in general so far, then we can work out the probability that x is greater than x minus 1 and less than or equal to x, and that is f, my distribution function evaluated at x, minus the same function evaluated at x minus 1. And if x can only assume integer values, what is this probability equal to? If x can only assume integer values, what's a simpler way of expressing the probability that x is greater than x minus 1 but no greater than x?
Equal to x.
That it's equal to x. So this is true in general, but if x assumes only integer values, this is the mass function. So from this distribution function, if we have it, we can get the probability that a random variable exceeds some value, that it lies in some range, or in the integer case, that it has some specific value. That's nice. Okay. Couple of examples. Switch back to the Christmas season is approaching. A red and green blackboard would be a nice way to start off the holidays. So I'm now at, number 10, I think. Yes, number 10, distribution examples is coming up. This first example, that doesn't show? Nope. try blue. That good?
Yeah.
Okay. We'll roll 4 dice. And we'll roll 4 dice. And the random variable, capital X, is the number of times 5 or 6 occurs. So basically, we're interested in an event that occurs with a probability of 1/3. Let me get this started, and you can look at the outline for the complete details. This is the probability that the number of 5s and 6s is less than or equal to 0. And the only way that can happen is if it's equal to 0, there's a 2/3 probability of getting a 5 or 6, of getting something other than a 5 or 6 on any individual die. So the probability of getting no 5s or 6s at all is 2/3 to the 4th power, which is 16 over 81. Now I want f sub x of 1, and here's where things get messy. This is the probability that I get either 0 5s or 6s or 1 5 or 6, and there is no formula that gives me that. All I can do is add the two terms together, and when you do the homework, you'll encounter all sorts of problems involving the probability of walking on 6 pitches and other baseball-related stuff that works the same way. There are a lot of these cases where the problem's easy to state, and the only way to get the answer is to add things together. So this is the best I can do. I take the probability of less than or equal to 0 and then add the probability of 1, and I've got less than or equal to 1. So this is the 16/81 that I already started with, plus the probability of getting precisely 1, 5, or 6. There are 4 choices for the roll on which I get the 5 or 6. The probability of that is 1/3. The probability of getting a 1 through 4 on the other 3 rolls is 2/3 cubed. So this is 16/81 plus 32/81, and it's 48/81. And I've worked all these out in the outline. Eventually, I get f sub x of 4. And what does that have to be equal to? This is the probability that if you roll 4 dice, you will get a 5 or 6 on 4 or fewer of the 4 dice. That's 1. So this distribution function always starts at 0 and steps its way up and ends up at 1. Yes, Jerry?
It's a Bernoulli distribution, isn't it? So many successes in 4 trials.
That's binomial. Bernoulli, yeah. This is the distribution function for the binomial distribution, and it's unfortunate that the term distribution is used for this type of function and then used generically as in binomial distribution and Poisson distribution, because the word means something subtly different.
Well, I've learned this to be the cumulative distribution function,
Cumulative
which is more
distribution.
descriptive.
Yes, but that's not what our textbook calls it. Cumulative probability distribution is the term that I would prefer. But distribution function is the standard term. I should say, the great thing about these distribution functions is they work equally well in the discrete and continuous case. So if this were a course that tried to treat even-handedly both discrete and continuous probability, I'd want to use distribution functions a lot, because they will work in cases where neither a mass function nor a density function is appropriate, and they would allow me to state lots of things in general that otherwise I'd have to subdivide into 2 cases. Okay, one more. Now here, this is a typo. There's a typo in the notes on this last one, and I have fixed it and put a revised version online, but I put a 1/3 in where I should have had a 2/3 as the probability of rolling something other than a 5 or 6. So this is the rest of number 10 done correctly. So here goes. Here's the deal. I'll roll a die until I get a 5 or a 6, and capital X, a random variable, is the total number of rolls. Which, in my opinion, was already implied by the statement, by the use of until rather than before. Okay. This is a case where we can actually write down the distribution function. The distribution for this random variable is the probability the total number of rolls is less than or equal to x. That's 1 minus the probability that the total number of rolls is greater than x. And this we can work out quite nicely. In order for the total number of rolls to be greater than x, that means I have to have rolled the die x times without getting a 5 or 6. That means on each of my first x rolls, I have to roll a 1 through 4, which happens with a probability 2/3. And that's where the typo in the outline is. It's bad in the handout I gave you. It's fixed on the latest version that I put online. Okay. One more little example just to finish up this outline, and then I'll have a few minutes to show you some stuff on the computer. So I'd like to do number 11 now, functions of random variables. And tonight I've just been building up machinery. Next week we will start with expectation and discover that the use of these random variables enables us to calculate lots and lots of things of some practical interest. So this is one last fussy topic that's necessary. Function of a random variable, written like this, y equals g of x. And this is just plain old vanilla composition of functions. This says, take your outcome, apply the function x to it to get a number out of it, and then plug that into the function g to get another number. Now here's the formula. And this is incomprehensible without an example. You might ask, if I define a random variable like this, how do I get the mass function for the new random variable? And you might think that it was some simple formula involving f and g, and it does involve f and g, but it sure enough isn't a simple formula. Here's why. What is this? This is the probability that the random variable y, which is simply the result of taking the random variable x and applying the function g to it, is equal to the value little y. And how on earth do we figure that out? Well, the only way to figure that out is to ask the question, what are all the values of x with the property that g of x is equal to little y? There can only be countably many of them, thank goodness. And what we have to do is take all the values of little x that have the property that when you apply g to that value, you get little y, and add up the probabilities for all of them. So this is the right way of combining this g and our original f. I can write this like that, and I still need this awful way of trying to indicate what I am summing over. This is the reason that I always like to subscript these things. This function and this function are quite different, but the conventional way of telling them apart is by the subscripts capital X and capital Y, not by giving them different names like F and G and H and so on. And if you drop the subscript, you totally lose track of which of these mass functions you're talking about. Now, here's an example. This example is slightly changed from the notes because if I use 3 coins rather than 4, it is both simpler and more interesting. So my example is toss 3 coins, and X is your payoff, which is calculated as +2 for a head, -1 for a tail. Very straightforward example of a random variable. The outcome of this experiment is a certain sequence of heads and tails, and this payoff rule turns it into a number. So let's make a table. The number of heads can be 0, 1, 2, or 3. What is, oh, I should associate a probability with each, too. What's the probability of getting 0 heads when you toss 3 fair coins? 1/8. Same for 3 heads and 3/8 for the other 2 cases. Okay? Now let's write down the value of X. If no heads come up, what's your net winnings from this?
-3.
-3. If you get 1 head and 2 tails?
-1.
0.
0.
+2 for the head, -1 for each tail. If you get 2 heads, you come out ahead by
3.
3. And if you get 3 heads, you hit the jackpot and you get 6. Now I can work out some functions of X. And, well, here's a rather stupid one. -X. This is actually the payoff for the sucker who's playing this game against you. Right? Just reverse it. Here's another one that's a little more interesting. The maximum value of 0 or capital X. In this case, what's the maximum of the 2 numbers, capital X and 0?
0.
0. So here's a case where we can apply our formula. For this random variable, what is the probability that it equals 0?
1/2.
1/2. And I'm using that incomprehensible formula, which means simply find all the outcomes for which the value of this function is 0 and add up their probabilities. Here's another one. Absolute value of X. So we say, well, just to make the game more fun to play, if you're going to lose a certain amount, you'll win that amount instead. That'll make it really fun. Now you get 3, 0, 3, 6. What's the probability of winning 3 when you play the game with this function of X as your payoff rule? It's 1/2 again, adding that and that. And finally, the sine function, SGN, which is minus 1 if x is negative, 0 if it's 0, and 1 if x is positive. What's the probability of the function what is the probability that the function that indicates your payoff is positive is plus 1? 1/2 again, adding these two together. Okay, now if I can switch over for the last, I've got about 10 minutes, do I? To the computer screen. So here's the deal on these computer assignments. First, none of you are required to do them. You are very strongly encouraged to do these if you are contemplating getting an extension school master's degree in some field that has to do with computers, because computer science courses don't give you much of a chance to do programming that has much mathematical content to it. And this will be one of your best opportunities to do so. So just as part of a well-rounded background, you'll want to do this. And let me tell you, I supervise a fair number of master's theses. I don't want to supervise your master's thesis unless you can do this sort of program and get it coming out fairly nicely. And if you decide you like PHP, I'd be thrilled to supervise your master's thesis, because I find that things that people do in PHP are generally useful, especially to me. So here is an example of something that you get straight from the download off the internet. This indicates 3 random numbers. It's actually simulating the rolls of 3 dice. And a cute thing about it is it looks like a web page, but every time I click reload, it comes up differently. And that's because this is being generated on the fly. PHP is a language that has many of the nice features of object-oriented languages like C++ and Java, but basically it's a web scripting language, and my computer is running both as a client and as a server. What I did before coming here was to put on the course website all the files I was planning to put on a CD except for the Netscape stuff. I think Netscape would get upset if I copied their install stuff onto the Harvard website. And having Netscape is optional. The only reason I suggest Netscape is I test things with Netscape. I don't test things with Internet Explorer. And there are certain things involving MathML that I know fail with Internet Explorer, but we're not planning to do any of these. So I have every reason to believe that this stuff will work with any standard browser, and there's not much of a need to worry about it. Okay, here is what I'm going to try to do. Well, the first question is always, will the Harvard network work? I'm going to see if I can get a wireless connection. Well, that's a good start. So you go to the course website. And you will notice now on the left there's PHP Setup 2005. I created that late this afternoon by copying all the stuff from the CD that I was planning to make 20 duplicates of by hand. These are the instructions exactly as distributed with the last packet of materials. So these are here, but they're redundant. You already have a hard copy of this. This is the version of EasyPHP that I'm using. I think it's still the latest version, but if there is a version 1.9 out, use 1.8 instead, because I test things with this version, and every once in a while they introduce a new feature that breaks things. This is one of the great deals of all times. Talking about a great deal when something is absolutely free, it's a little hard to compare. But you download this, you get three things. One, you get an Apache server running on your machine, and there are disclaimers about how this is not a professional quality server and so on, blah, blah, blah. But the fact is, I have been using this server for 2.5 years now with Windows XP Home Edition, and I have about a tenth as much downtime as any other server that I know of. So for light usage, this is a perfectly good server, and it's absolutely free. You also get this wonderful PHP scripting language with a fabulous online manual, so good that you needn't bother to go out and do what I did and buy lots of books on it, because the manual's better than the books. And you also get, not that we'll be using it, MySQL, which is a perfectly good and totally free relational database, which is the underpinning of the online placement tests. Everything in the online placement tests was done with this free system, and I think we still haven't upgraded to anything you have to pay for. So that's this. This is a nice little editor. Just unzip it and set up a shortcut to it on your desktop. If you use a Mac, you'll need something else in place of this. This comes in Mac and Linux flavors as well as Windows. This is very specifically a Windows editor. Both these things were done in France, and every once in a while you'll get error messages or welcome screens in French. Don't let it bother you. You have the opportunity to set the language to English more or less everywhere. And this is the PHP online manual. So all those things you could just have gone out onto the web to get. The one you can't is this stuff. This is specific to me, and now I'm going to try downloading these things. If you just click on them, they open, and at that point, saving becomes a bit risky. So I right-click and do Save Link Target As, and I will create a new folder called Graphics, which is what I proposed to you. Save it. This one I had to be really clever. I went to upload it. It said, this is not a type that's usable by students. We won't upload it. So I renamed it to .text, uploaded it as .text, and then renamed it when it was on the site. And you can download it. There it is. This contains all my primitives for handling geometry. You'll need to understand about 2% of this, and the 2% is right at the end. And finally, this is what passes for documentation for the geometry file. Okay. Now, let's see if this works. I have already installed EasyPHP on this computer, and I have to start it up. I start it up by clicking on this, and you see the E with the red dot flashing. When the red dot is flashing, when your server is running. If you don't see the flashing red dot, your server isn't running. Once the server is running, Netscape thinks that this strange URL is just like anywhere else on the web, but the name is localhost. That means it's a server running on your own computer. And this little web page is working fine. Now, everything is on my computer. My computer is running as a server and displaying, and the browser is going and looking at that server, downloading this web page, and displaying it. So that's the first thing. Now, just to finish up, how long have I got? 3 minutes. Okay, just the time I need. If you look at your instructions, I will show you just a couple of other things. So this follows the homework. I point this out because there's some fun stuff you can do for next week just to get started. I've gone through step 3, 4, 5 in advance. I've done 6. I have installed HapEdit, and I'm ready to show you what happens with step 7. So with step 7, I launch this nice little editor called HapEdit. And I will close this one, which I had open earlier. And what I need to do is associate a HapEdit project. Remember that folder graphics I just created? So I say add project, and it says where do you want the projects? And I navigate, 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 and there it is. Okay, so that's graphics. And I double-click this project. And what do you know? It shows me the 3 HTML and PHP files that I copied in there. And I can now look at bargraph.php. And this really isn't very hard to understand even if you've never seen PHP. I'm including this geo class, which has all the geometry primitives in it. I'm setting a couple of variables. In PHP, variables have to be preceded by $signs, and they turn green in this editor. And I'm saying this could be passed in from outside, in which case I want to use that value. Otherwise, use the values 6 and 50. This says create an object called a canvas, which runs from x and y ranging from minus 0.5 up to max val plus 1, which is 7, with this scale factor and these red, green, blue values for the background. On that canvas, plot an x-axis, plot a y-axis, start out the random number generator, and then call the fill horizontal bar function in the canvas using the specified colors, the specified locations, and most importantly, using the Mersenne twister random number algorithm to generate a random number that is equally likely to have any value between 1 and 6 inclusive, and then write the captions red, green, and blue on that. After you've done this, slap on a header claiming that this is a PNG, portable network graphics file, and display it. And here's what happens. When I hit F9, this is sent to my browser. The browser runs this code, which has the effect of generating an image. It then displays the image. And it wants to, you always type in the same thing here. There it is. So that's the effect of running that PHP script. It builds up an image with these colored bars in it, using random numbers for the right-hand edges of the bars, and then it displays it. And when I hit reload, it reloads the page, reruns the script, runs the random number generator again, and gets different random numbers. So this is a very simple way of doing this. Have I got any time left? I've got a fraction of a second left. Okay, so what you can try doing is first follow the instructions to get this working, and then try making one trivial change. You can open up, we may run off the end here, but it's all written out. Open the file geoclass.php. You can ignore most of this. But down at the end, you will see that in addition to the function fill horizontal bar, which I was using, I have a function called fill vertical bar, and I would suggest playing around with this to see whether you can get the display working with the bar graphs vertical rather than horizontal. If you manage to get something working and make one trivial change, in my opinion, you are roughly halfway to mastering a new piece of computer technology, and you can turn that in with your homework next week, show that you're underway on this. And then the project involves generating displays for lots of different distributions, calculating expectations and variance. Ties in beautifully with the subject matter over the next 2 or 3 weeks. So if you do this, you will not only master a new computer technology, but you'll get an enhanced understanding of the subject matter of this course.